Okay, so it's 5 minutes past 4. I'd say let's start. Hope you're ready. So today's lecture will will be something new. It will be about quantum cryptanalysis, and so I will try to explain or try to convey the idea of quantum computing, and also explain some method or algorithm we can use in more detail. But first, a small introduction or an outline on what I'm going to talk about today. So first, why should we even care about quantum computing? Why is that even important? And of course, this is the motivation behind that. And then I'll also talk about the properties of quantum computing. So what things which things are different than actually they are in classical computing. And after that, so originally I wanted to focus mainly on the cryptanalysis part of quantum computing, but I then realized that this is quite hard without actually also explaining some of the basics. So after that, I will explain these basics. So this will be the first part of this lecture maybe, and this will be about quantum computing. And in terms like qubits or superposition, you may already have heard about them, but now we'll try to explain them in more detail. And finally, we will also talk about quantum gates, which are actually quite similar to classical gates. And what they do or what they are needed for is actually that we can compute something on a quantum computer. And then finally, so this is basically the introduction and the background part. And finally, this will be then the second part of this lecture. I will talk about quantum algorithms, and in particular two of them, so Grover's algorithm and Shor's algorithm. But 80% approximately of the time will be spent explaining Grover's algorithm, because I actually want to explain it in more detail. And so maybe can get an idea how this actually works on a quantum computer. So don't worry if you don't yet know what a Grover or Shor algorithms, what they do. So I will also come to that later. But okay, so first a small introduction. So why should we even care about quantum computing? And now I think it's a common belief that, and nearly everyone maybe would respond it that way, that quantum computing is faster. And this is somehow of an oversimplification. It can actually be much faster, but actually it's not always faster. So there are some operations which are very similar on a quantum computer as they are on a classical computer. And one example is addition, and more specifically binary addition. So there are some tricks we can do with integer addition, for example, with the carry bits and so on. But for binary addition but the simple operations in general, a quantum computer is actually similar to a classical computer. However, for some operations, it can be much faster than a classical computer. And these situations are sometimes related to some specific problems. So for instance, one of these problems is integer factorization. And integer factorization is something, if we could do this very fast, it would be nice if we want to break RSA, for instance. And in that case, actually, so if we want to use a quantum computer, in that case, it can even be exponentially faster than a classical computer, which is a huge speed up compared to other speedups. Okay, so this is a motivation, and we know that a quantum computer can actually be exponentially faster for some algorithms, and actually this is exactly why we should care, because many currently used protocols rely exactly on concepts and on underlying strategies which can be broken much faster when we use a quantum computer. And this is especially true for some public key crypto schemes, for example for the RSA, but it's also true for symmetric key crypto schemes. But we believe, and this is something we hope, that for symmetric key primitives, so they are probably not as badly affected as for instance, RSA. But still, we can also use quantum techniques to break symmetric key crypto faster than with a classical computer. And one approach which does this will be explained later in this lecture. So this is one method. We can use a quantum computer to actually break something, but we can also use a quantum computer within security protocols. So maybe we can use quantum operations to make to implement actually secure crypto protocols. And finally, what we can also do is we can try to build algorithms, so classical algorithms, which use classical operations, and that are secure with respect to quantum attacks. And this actually leads me to these distinctions, which, well, is the title of the slide, so it's not all the same, because when we talk about quantum stuff in cryptography, we often talk about quantum cryptography and post-quantum cryptography, and one may think that that's all just different words for the same thing, but this is actually not true. So usually when we talk about quantum cryptography, we mean that we try to use quantum phenomena in order to build crypto systems. And one example is quantum key derivation, for instance. On the other hand, if we talk about post-quantum cryptography, we usually mean protocols which are secure against quantum attacks, but which do not necessarily use quantum phenomena themselves. So if you remember, there was the lecture about asymmetric primitives in the cryptography course from last term. And in this lecture, there were mentioned some post-quantum competition, essentially a NIST competition. And in this competition, the goal is to actually find some classical algorithms which are still secure if we assume that quantum computers are available. And some of them are, for instance, based on lattice-based schemes, or are lattice-based schemes. So these are two things we can do. So these are a bit different. So quantum cryptography and post-quantum cryptography. And finally, this is then, which will be the main topic of today's lecture, there's also quantum cryptanalysis. And in this category, basically, we try to attack cryptographic schemes with the power of quantum computers. So we use quantum computers, so quantum techniques, to try to attack cryptographic schemes. And two examples for these algorithms are, for instance, the Grover's algorithm, but also the Shor's algorithm. And we'll see in detail what is targeted by these algorithms. So are there any questions so far? So this was only an introduction, nothing really specific so far, just some terminology. I will wait a few seconds. Okay, so if there are not any questions, great. Then let's start with the more interesting stuff, maybe, with quantum computing. As I've already mentioned before, this chapter will be about basically the background, and we will use this background to then explain a concrete implementation of a quantum technique. Okay, so quantum computing, but let's first start with without any quantum stuff. So let's just start with the classical setting, and in the classical setting we only have a single and a very simple bit. And I'm sure you already know this. A bit can be either 0 or 1. But let us assume, just for the sake of this explanation, let us assume that we define the 0 bit by this tuple or vector, by this column vector 1, 0. And let us also assume that we define the 1 bit by a similar vector, but we flip the entries, so we define it by 0, 1. And now this may not make any sense to you, or you may even think this is useless because we can just use 0 and 1 directly. And if we talk about classical bits, it really is useless, but it will help later to understand the concept of the quantum equivalent of a bit. So let us just define a 0 bit is defined by 1, 0 by this vector, and the 1 bit is defined by 0, 1. Okay, so we can ask ourselves which operations operate on a classical bit. And now it's important to say that we mean an operation which takes one input bit and which produces one output bit. So for instance, an AND gate is not such an operation because it takes 2 input bits. And it turns out that there are exactly 4 operations. There's the identity, which basically doesn't change anything. So a 0 remains a 0 and a 1 remains a 1. Then there's also the negation, which essentially does the opposite. It flips the bit. And then there are the two set to 0 and the set to 1 functions. Essentially, the set to 0 function basically sets the output bit to 0, regardless of the input. And the set to 1 function does the same, but it sets it to 1, regardless of the input. Okay, So very simple, we have two vectors, these define the bits, and there are these four functions basically that operate on a single bit. So we have these four functions. Let us go one step further now. But still, this is all classical, no quantum stuff related here. This is all classical still. Okay, so for the identity function, we have this vector. We need some way to basically map these functions. So all of these functions are linear, of course. We need some way to map this, to basically represent this identity function by a matrix. This can be done because it's linear. And indeed, this is very simple in that case. We just take the identity matrix and we see that if we multiply the 0 vector, so the vector which represents the 0 bit, so we do this for the 0 bit here, then the result is again the 0 bit, and you can try it with the 1 bit, it's essentially the same. And for negation, it's very similar. We flip the entries in the identity matrix basically, and what happens is that the bits here get slipped. So the vector representing a 0 gets the vector or becomes the vector representing the 1 bit. So this is the operation here. And very similarly, for the constant functions, we have, well, this matrix here, which is basically used to create a bit which represents a 0 regardless of the input. So you can try making it with 0, 1. Then we have here still a 1 and here still a 0 due to the multiplication here. And the same happens essentially for the second constant function, for the set1 function, where basically we just move this float below here, and then we create a 1 here. So this is all still classical. And are there any questions to this? Okay, then we'll move one step further. So we can now try to identify these four functions by different properties. And we see immediately that the identity function and naturally also the negation, then they are reversible. So this means that basically if we are given an output value, we can uniquely determine the input value. And we can also see this by just having a look at the matrices here, and we see that they're invertible, so the operation is also invertible. But this is not true for these constant functions here. So these set to 0 or set to 1 functions, they are non-reversible, which means that if we are given the output, we cannot really know what the input was. And in the case with the single bit here, if the output was 0, the input could have been either 0 or 1. We just don't know. And indeed, the matrices here are not invertible here, which we can see immediately. Okay, so we have two functions, identity and negation, which are reversible, and we have another two functions which are non-reversible. How does this relate to quantum? And this is now the first time this quantum word is mentioned. Well, this is actually one of the biggest distinctions between quantum computers and classical computers, and this is a very, very crucial difference. Namely, on quantum computers, we can only use reversible operations, except for the final measurement. I will also come to that later, what this means on a high-level way. But essentially, in quantum computers, we can only use reversible operations. And if you think about it, if you have your typical C program or Python program or whatever on a classical computer, and if you take a look at what you actually do, you will see that many times you actually use functions which are non-reversible. And so this is a very, very big difference. And why is it the case? Well, it's related to the unitarity principle in quantum physics, quantum mechanics, and it's also related to the amount of energy which is lost if we actually apply a non-reversible function. Because if you think about it, if we apply a non-reversible function to some input, that actually means that given the output, we cannot regain the input anymore. So what we are doing is we actually destroy information. And this destruction of information costs some amount of energy. And in quantum computers, it's quite fascinating that we could, in theory, implement such a circuit which does not dissipate any amount of heat. So this is a very abstract concept, but it's a very, very crucial difference to classical computing. So this is the first thing here. And throughout this presentation or lecture, we will deal with various quantum gates and various things we do on the quantum circuit. And all of that will actually be reversible. So that's very important to know. And we will also see this later. Okay, so the first big difference. So let's move on. And now we actually introduce this new concept of qubits. And so until now we had classical bits, but now we have something new, which is a qubit. And the nice thing is, and this is also why we defined these bits by these two vectors, which we don't really need to do in the classical setting, but here we need to do that. The nice thing is that actually we were already using qubits. So let me formalize this, so state more formally. Qubit is something which is both 0 and 1 at the same time, but each with their own probability. And now it's very important to understand that a qubit is not 0 or 1, and we just don't know what it is, but it really is both 0 and 1 at the same time. So there's a difference. So this is the fascinating concept about that. And to each of these values, so 0 to the 1, we assign it a probability. So in physics, such a qubit can be built, for instance, by using the properties of electron spins or particles. But we will not go into that here in the lecture. But just know that a qubit is something that represents states, basically. And it assigns a probability to each of the states. And each of the states is actually active at every moment. So if we do this with two vectors, we can think about a qubit being this combination here, where basically the x1 state is assumed with a probability of alpha squared. So this is a weight, we can also say. And this x2 state is assumed with a probability of beta squared. And so the total probability, the probability has to be 1 in total. So basically we have alpha squared plus beta squared. Beta squared has to be 1. And this generalizes also to more probabilities we will see later. But this is the simplest case with just one qubit. And this thing here, so basically having different states with different probabilities assigned to them, this is what is called superposition. So now we also have this term here. This is a superposition. And the thing about this superposition is that once we measure the state, so once we try to figure out in which state the qubit or a combination of qubits actually is, once we do that, we destroy the superposition. And what then happens is that the state collapses, so we don't have a superposition anymore, we have a specific output, but, well, we have a specific output, so we then know the state. And the thing is that this measuring the state is usually done at the very end of a computation. And now it's also somehow fascinating that during a quantum circuit, some quantum algorithm, it's usually the case that we don't know which state is assumed at each particular step. We just do the computations without even knowing the intermediate states. But at the very end, we then measure it, and we hope, basically, that the weight associated to our answer, or to the answer we want to have, is so big that that's the most probable answer. So the answer with the highest probability, maybe intuitively. We will see later why this is why this actually works. This is the fascinating difference here. Okay, is there any questions to this? Are there any questions to that concept? Okay, so let's move on. Now we have a single qubit. A single qubit can denote two states, but of course, if we want to have something more than that, we need something more, well, and we need, in that case, more qubits. And it's nice because we can actually build combinations of qubits, and they are denoted using so-called tensor products. And we'll see here what this actually means. So just to illustrate that, let us have 3 qubits, x, y, and z. Then basically what we do is, so these are the weights, so to say, and these are the associated states. So what we do is, basically we multiply x1 by y1, y2, we multiply x2 by y1, y2, and then we get this vector x1, y1, x1, y2, and so on. So 4 different states. And we can also do this with 3 qubits and so on. And there's a question, sorry. No, you actually, no, yeah. No, I don't think you misunderstood. It's actually correct. So the answer we get is not directly the probability, but it's based on a probability. So for example, if we have the final superposition, which has a probability of 100% at the correct answer, then we get the correct answer with a 100% chance. So we don't get the probability really, but we get the answer with, we hope at least, with the highest probability. So that's the relation between the weight and the state. So the state is actually the answer we want to have, and the probability is just the weight associated to this state. So what we try to do in a quantum circuit is just to make the right probability at the right state large enough until the end. So this is what we try to do. Good question, yeah. Okay. So yeah, we can do this tensor product also with 2 qubits, but also with 3 qubits. And of course, if we do that with 3 qubits, we will end up with a vector which contains 2 to the power of 3, so 8 states. And this is also something that now may remind you of something, because if we use more and more qubits, this vector here gets exponentially larger. And this is actually what's exploited in in quantum algorithms in general. Because if you use n qubits, okay, if you use n qubits, then this vector will contain 2 to the power of n states. But actually a superposition of 2 to the power of n states. So actually, we have a vector which basically is assuming each of the 2 to the power of n states simultaneously. And this is not true, of course, if you use just n bits, because if you use n bits, we have a single state, a single one of them we can encode. But here with n qubits, we can actually encode or use all of these states simultaneously. So that's the power here of these qubits. Yeah, and there's actually also a slide with Schrödinger's cat coming up. I thought yeah. Okay, so what we will also see is that if we use concrete bit values in these vectors here, we will end up with concrete bit values also here, which I think we will see it now. Yeah. But first about the notation. So we have been working around a lot with vectors here, and it's a bit cumbersome to always be writing down vectors. So we have this thing which we call Dirac notation or bracket notation, and in a simplified manner, how this works is we basically write, for instance, the 0 bit as this cat. So this is actually cat. Sorry, no, this was a spoiler. So this is actually a cat, but what we can do now, we can write 2 zeros, and this basically means the tensor product between these 2 qubits, which again gives basically a vector containing 4 states. And now just to show you, we have here filled, let us assume these are weights here, we have filled in concrete values, so 1 and 0, not something like between 1 and 0. So what this means is that this qubit, if this was a weight here, this is a bit simplified, that this qubit here assumes the 0 bit 100% of the time, because the 1 is here, the 0 is here. So there's a 0% chance to result in a 1 bit and a 100% chance for the 0 bit. And that's the same also for that one. And what this means actually, if the first bit has a 100% chance of being a 0, and if the second bit qubit, has also a 100% chance of being a 0, then essentially the final state has a 100% chance of being 2 zeros, to 0, 0, essentially. And that's also what this vector is here, because essentially this denotes the first state we can build with 2 bits, 0, 0. This is then 0, 1, 1, 0, and 1, 1. And you can do the same here. So basically, if we assign these values here, then this state, or this vector here, has basically a 100% chance of assuming the state 1, 0 at the end. So are there any questions to that? Okay, so this is not really very important now, but we will also see it later. Usually if we have some operator h which acts on this vector of qubits, so we write v just a vector of qubits, think of it as actually being the tensor product of multiple qubits, but this is just shorter. And if we have an operator h which operates on them, then basically we write h cat and this vector. And yeah, as promised, now comes the Schrödinger's cat. And this is actually not related to this cat notation here, at least I think it's not. Probably you remember Schrödinger's cat, right? And she's both alive and dead at the same time. So let us denote the alive state by this cat symbol here, and let us denote the dead state by this death or something symbol here. And now what we can do is we can denote the state of the cat using this Dirac notation. Namely, we have a weight vector, so let us just assume it's 1 over square root 2, 1 over square root 2. And if you remember, this squared plus this squared has to be 1. And at least so it's 1/2 plus 1/2 is 1. So this is the weights vector, probabilities vector, and this is the state vector, right? So this is the bra, this is the cat, so to say. And if we actually do the multiplication, we see that this is the result. And what this means is that the cat is both alive and dead at the same time. And in that case, with these weights here, with the same probability. Yeah, so this is essentially Schrödinger's cat in cat notation using a qubit. And what we can also say is now about the measuring result. So if we measure the state, then we will get one of the answers with the same probabilities, each of the two. And basically measuring will collapse the state, and we then know the fate of the cat. So this will decide the cat's fate. Okay, so this is the same as before, just with maybe a more intuitive notation. Okay, so let us move on. Quantum gates. So this was about qubits. Now what can we actually do with qubits? Well, we try to somehow transform them using quantum gates. But we have to recall that each operation has to be reversible. We are in this quantum computing model. And then quantum gates are essentially invertible complex square matrices. So of course for this property they have to be square. And sometimes you also like to work with complex numbers, so there are also complex matrices, but we will avoid this here in the follow of this. So in the next part we'll keep it simple, I think, I hope. Yeah, and they need to be invertible. There are also some additional properties, we don't need them right now. And essentially then a quantum gate operates on a vector of qubits. So this is what a quantum gate does. But actually it operates on the tensor product of multiple qubits. So yeah, and in physics, so this is the matrix representation, of course, but in physics, so in an actual implementation of quantum computer, this translates somehow to, and yeah, this is a simplification, of course, but it translates to a gentle touch applied to the qubits. And this gentle touch maps some operation. And the important thing here is that this touch has to be gentle enough such that it doesn't make the state collapse. Because if it collapses, we basically destroyed every information we had. So we only want to do this at the end of the computation. What this means, and I think I've already said this before, what this means is that during this computation with quantum gates, we don't know the state after the operation. We know the superposition, we know the weights, but we don't know the precise state it assumes. So this is about quantum gates, essentially. And now let me give you an example of a quantum gate. So there are many more quantum gates, but this is probably one of the most essential ones. And this is called the Hadamard gate, or H also often. And this is often applied as the initialization step in the beginning. And why is it applied in the beginning often? Well, because intuitively it transforms a deterministic state, or some qubit which has, for instance, a 100% of being zero, which transforms this into a fluid one, and precisely into one where the probabilities are uniformly distributed. So this is the matrix. Of course, we need a -1 here, otherwise it's not invertible. And for example, if we apply this Hadamard gate to the zero qubit here, so this qubit which is 0 with a 100% chance, we basically have this operation. So we have the Hadamard gate times this vector here. Again, it's a bit simplified because we ignore the state and only probability here. And then the result is this vector of weights, of probabilities. And we can see that previously it wasn't uniformly distributed. So we had a probability of 1 that this was a 0. And now we basically have a probability of only a half that it's a 0 and a half that it's a 1. So this is what the Hadamard gate does. This is now applied only to a single qubit. Later we will apply this to the tensor product of qubits. But essentially the notation is the same, and also what happens is very, very similar. Okay. So a very short intermediate summary, because this essentially concludes the first part of this lecture. So we know that qubits are very similar to classical bits, but they're in some superposition. And the combinations of multiple qubits are tensor products. So these are basically not multiple states in superposition. And we use now these quantum gates to compute with qubits on quantum computers. And there are many different quantum gates. There's the Hadamard gate, there's the controlled NOT gate, there's also the Toffoli gate and the Pauli gate, and there's even a quantum Fourier transform gate, which we'll use later but not explain in detail. So there are many, many different gates, and remember that each of these gates has to be reversible. So this is the thing we work with in quantum computing. Yeah. Okay, are there any questions to this first part of the lecture? Okay, then let's move on. So what we will now do is basically we will first hear something about a very concrete quantum algorithm, and we will then apply the background we now heard about in order to understand how this algorithm actually works. And so most of the time in this chapter will be spent on this Grover's algorithm, because I think it's a very intuitive approach, and it explains nicely the difference also between a classical computer and a quantum computer. Okay, so first a bit of a background here. It was first presented in 1996, so it's not so new, and it's essentially a search algorithm. So what it does is that given some unsorted list of length L, so we have of length n, sorry, given some list of length n, we try to find a special item x star. So equivalently, we try to find first if this item is in the list, and then we also try to find the index of this item, so where it actually is. And now you may think, well, this has nothing to do with cryptanalysis. This is just a search algorithm, and actually it can very, very easily be mapped to a function which basically finds a block cipher key or a hash per image. But more on that later. So this is actually the easy part of that. Okay, so to understand first the difference between the classical search in a list and the quantum search in a list, let's assume the hardest case, the hardest possible case. And the hardest case is, of course, if this unique item we want to find is, so if it's unique. This is the hardest case. Why? Well, because if we have multiple occurrences, then the probability to encounter this item is larger, of course. And we can think about it, how many trials would we need on a classical computer? How many trials would we need if we are given a list of length L? Well, we are some element, so the linear complexity, some element in ON, but actually after about half of the trials, you would expect to already have it encountered, this element, to already have it, and then the probability basically starts getting smaller and smaller to not encountering it. However, so this is linear complexity. However, on a quantum computer, the nice thing is that we have only a square root of n as the complexity. So this is a quadratic speedup. So if you think about it, if we have, so this may not sound very crucial, or it's not an exponential speedup, but if the list has 1 million elements, we would expect that we find a unique element on a classical computer after around 500,000-600,000 trials. But on a quantum computer, we actually expect to find it after only 1,000 trials. So it can be a huge speedup, and yeah, so it depends on the perspective, I guess. But that's essentially the difference between the classical computer and the quantum computer. However, this doesn't explain anything, right? So why do we only need square root n trials? So this is the main question here. How does this work? Okay, so first some preliminaries. Let us define the goal again. So we have some unique element x star in this list. We assume that it's so unique, it's the only one. We don't have another one of that. And assume that we also have some oracle function. I will come to that later, what this oracle function actually is. And again, this is so this will be done quickly then later. But assume we have some oracle function which basically returns 1 if the input is this element we are looking for, and which returns 0 if the input is anything else. So any element we are not actually interested in. And so this can be implemented very, very easily actually on a classical computer, but also on a quantum computer, we assume that. And what we further assume is that we have a list which has capital N elements, and that capital N is a power of 2. So this assumption is just for the sake of the explanation here. But what this means is, if we have a list of 2 to the n elements, so 2 to the power of n elements, this means that if we use n qubits, so small n qubits, then the superposition of these n qubits is sufficient in order to denote this state vector, which contains every possible n-bit index. Okay, so basically we have a huge state vector which has 2 to the power of n, or capital N, entries. And for that, we only need small n qubits. So this goes back to the tensor product before. So that maybe gives already some hint at the power of a quantum computer, because this, of course, this wouldn't be possible with a classical computer. Okay. And further, let us assume that the starting state is, we have some starting state, we have a weight vector and a state vector in Dirac notation, so behind the cat. And this alpha denotes the amplitudes. We will see now why I'm actually saying amplitudes. And so they're essentially probabilities. And x is a column vector of possible states, and just another way of writing this down is this. So basically we have a sum of alpha x times some qubit x for each x. This is just a different way of writing down. We did something similar for the Schrödinger's cat. Okay, however, to understand how this works is, I remember we need 3 building blocks. And I will explain these 2 building blocks now, so one after another, and they may not seem related, and they may not even seem to help. So this is just preliminaries, but then later we will see how they actually help us to get the result. So the first building block is phase inversion. Let us assume that our wanted element is x star, and we know, of course, that f of x star is 1 by construction. Now the phase inversion, or the purpose of this building block, is to invert the phase at the position of our wanted element. Now you may ask, well, but how do we know what the wanted element is? How can we invert the phase at exactly this position? If we would know it, we wouldn't need this algorithm, right? And well, the thing is that we don't know, but we apply a function which, without knowing, affects only this phase. And we will see later how this works. Okay, so phase inversion inverts the single phase. So what does this mean? Well, we have this input, this input here, where basically have the weights alpha and the qubits, the states x here. And for every state x, which is not our wanted state, the state we're looking for, okay, for every of them, alpha x just remains the same. Nothing changes. However, at the state x we are looking for, we invert the amplitude alpha. And maybe to show it in a graphical way, graphical representation. So if we have here only 4 elements and we're looking for a third one, for x, for 2 basically here, then if this is the input, what happens is that everything we're not looking for stays the same, so 0, 1, and 3, but the element we're looking for basically gets its amplitude inverted. So that's what happens here, x star. Okay, this doesn't help a lot, right? But let's see. For an example, so for instance, if we have if we're looking for the 2, like in this picture here, we're looking for 2, and the weights before the inversion are 1/2, so 4 times 1/2, and remember that this squared plus this squared plus this squared plus this squared has to be 1, so basically the probability for each is 1/4. Then after this phase inversion, we have the same vector but with a minus here before the second one. So basically we inverted this weight. Well, this is all nice, but still 1/2 squared is the same as minus 1/2 squared. What this means is that if we would measure the output state after the phase inversion, the probability of getting the correct or wrong answer would be the same as before. So this doesn't change anything, and so this doesn't seem to help a lot, right? Okay, let's just leave it there and focus on the second building block. So the second building block is called inversion about mean. And the thing is, so we are again given some input, and the amplitude mean, so this is now standard like in classical computing, it's basically the amplitude mean is the sum of all amplitudes, or the sum of all weights, divided by the total number of weights. So 2 to the n is actually capital N. This is always the same in this example. Now, what you want to do is the inversion about the mean. And it turns out it's this function. You can draw it, and we'll also see it later that this is actually true. So what you want to do is that every amplitude alpha x, or every probability, gets basically mapped to 2 times the mean minus this probability. And if this is fulfilled, then what is implied is that this input gets basically mapped to this output here, where every amplitude or probability is replaced by 2 times the mean minus the very probability here. And again, some graphical representation to make it more clear maybe. So let us assume we have this input here. So we have again only 4 values, 0, 1, x star 3. We have some amplitudes, probabilities for these values here. And well, let us say the mean is here. I think it's actually also precise, I think. So let us say the mean is here. Then what happens is, well, we basically compute 2 times the mean, which would be roughly eyeballing it now here maybe. And we subtract this amplitude, which makes us end up maybe here. And this is exactly what we have here. And we do this now for each of the amplitudes, and basically the distance here gets, the distance from the mean gets inverted. We see this here. So this, yeah. Are there any questions to this operation here? So I know that it sounds confusing and it doesn't really help a lot, but we'll see later why it helps. Okay, then let us move on, and now we combine these techniques. So what we first do is we start from a uniform distribution. What this means, we have a list of 10 elements. So 10 is not a power of 2, but well, I think it's enough here for a demonstration. So we start with uniform amplitudes, uniform probability values, which means that every output, every state has a probability of 1 over square root of capital M. So this is the starting state. Now the first thing we do is this phase inversion. And what this does is, well, we know it now, it inverts basically the phase of the element we want. Again, this is assuming that we know the element, or at least it seems so, but later it will be an operation which does not know the element. So this will make sense later, how this is possible. Okay, so basically we shift, so we invert the phase of this x star. So this is the second step, the phase inversion. And then the third step, the inversion about the mean, what this does is, well, we have a mean, and we basically invert this. So each of these elements here, each of these other elements or unwanted ones, gets a slightly lower probability, but the inverted one, since it's very far away from the mean, this gets a very, very significantly larger probability. Now, of course, with 10 values, it's significant. If we have many, many, many values, the difference here may not be so big after the first step. So this is the main idea. And then what we do is, so this is essentially all, what we do is we repeat steps 2 and 3, and eventually the amplitude of x star will be close to 1. Actually not close to 1, this is not so true, but more close to 1/2. So it will be much higher than the other amplitudes. That's the final result, which we hope for, not close to 1 actually. And yeah, I still claim that the number of steps is approximately square root n, and we will see now why this is actually the case. So this is all what is done here. So let us have a more detailed look. After the first step, we know that our wanted element has an amplitude of 1 over square root n. So this is all uniform, the same amplitude as for everyone, for every other element. And after the second step, we do this inversion. So the amplitude gets minus the same, so minus 1 over square root n. And finally, after the third step, we have 2 times the mean, and then minus 1 over square root n, so plus 1 over square root of n. However, we assume that we have many, many, many elements, so n is very large. So what this means is that basically the mean we input here, which is computed exactly like this, has in the first step 1 plus 1 plus 1 plus 1. This is the uniform amplitude of every unwanted element, so 1 plus 1 plus 1 plus 1, plus minus 1, which is this minus 1 here, but we have only one such minus 1 because we have a unique element we're looking for. And then again plus 1 plus 1 plus 1 plus 1 for every others. So approximately this sum here is n, approximately. So this whole fraction here will be approximately 1 over square root n. So what does this mean? Well, it means that our mean value after the first iteration is still very close to the uniform value if we assume that n is quite large. So what we see now is it's actually slightly slower, but it's very close to it. And what does that mean for our alpha x, for our weights? Well, every unwanted weight gets slightly lower than our original mean, and the difference is very, very tiny if we have a large n. But our wanted x gets much higher than 1 over square root of n. And what actually happens is, so of course in comparison, and what happens is that if we map our wanted x to this value here, which is basically inversion about the mean, we have that this is approximately, since this holds, this is approximately 2 over square root n minus 1 over square root n, so plus, which results in 3 over square root n. And now if we do this again for another iteration, we will have approximately 5 over square root of n. And if we do it again, we will have 7 over square root of n. And this approximation gets, of course, worse and worse the more we go forward. But it maybe conveys the idea that after square root n trials, we will be very close to a high probability here compared to all the other probabilities, even if n is large. So you can write this down mathematically, rigorously, and this actually holds. Good, so this is the reason, and for another iteration, it's basically the same. So almost all amplitudes are still just below 1 over square root n. So again, we will have a slightly smaller amplitude for every wrong answer. And again, our correct answer will increase, but much more than the others decrease. That's the thing here about this algorithm. And yeah, so the final thing is that we have a a probability of about 1/2 after square root n steps for the correct answer, and the amplitude of all unwanted elements then approximately that after square root n steps, which especially for large n is much smaller than the probability for the correct answer. So this is how that works in a sense. Okay, are there any questions to that? Okay, so if not, this was actually maybe the complicated part. Now it gets to the implementation part. So how do we actually implement this on a quantum computer? And so we have these two building blocks. We have the phase inversion and we have the inversion about the mean. But how do we implement that? Well, remember that for the phase inversion, we want to have that basically every input, gets mapped to this output where the phase is essentially inverted where the amplitude is inverted if f of x is 1, because this means that this x is the correct element. This is actually part of the trick why this function does not need to know the correct element, but just inverts the right amplitude here. Okay, so for every wrong answer, f of x will be 0. So basically we would have times 1. And for the correct answer, we would have 1. So basically the phase gets, the amplitude gets inverted. Okay, so if we think about that as a matrix operation, we may also write it down as this matrix here. But this is not really implementable in a quantum way, so we need some way to implement it. And now actually, this is the first time we see a quantum gate, or how it's usually defined, namely with this graphic here. So we have some function, an input, and an output. And remember that for each quantum gate, we need that it is reversible. So each quantum gate needs to be reversible. So what is usually done, and this function f, which returns 0 if the input is not the correct one, and 1 if the input is the correct one, is clearly not reversible. It's reversible in the case it returns 1, but in the case it returns 0, we have many possible answers. So this is not reversible. So what is usually done for these problems is that we create a circuit which basically gets the normal input, which we would have, and some placeholder bit or auxiliary bit. And this is initialized somehow, and actually it gets added the result here, the output, the final output. And what we do with the input, we just loop it through and we get the input at the end also as the output. So of course, if we output also the input, then the function is clearly reversible because we then automatically know the input. This is a trick which is basically used often to make a non-reversible function reversible in that case. This can be thought of a placeholder bit. Okay, but we don't want to have that one. We want to have this, right? We want to have this one. So how can we do that? Well, we can rewire the gates and say, well, we have an output here which is this, and now you have to trust me, it's a good idea to input this minus qubit here. And what this minus qubit is, well, it's actually the Adama transform to the constant 1 qubit, which means that basically it's this representation here. And this is somehow our oracle qubit, which is needed, and we will see now in the next slide, to basically toggle the output accordingly without actually computing this function, so this exponent here. So the purpose of this thing is to basically change the phase of our wanted item. And how can this be done? Well, consider this conditional gate here, which basically takes an input x and some placeholder bit b, let us take this b. And what this function does is that it returns basically the input as the output, so like here, input goes to input again. And then it returns this final position at the end, f of x, x or b. Okay, so we have this input and this output here, and b can be thought of as a control bit basically, which is added here to this function output here. Okay, if we apply that to the previous circuit, so we basically in the previous circuit have the input x and this minus bit, this is exactly this here. Okay, if we apply this to the previous circuit, we compute first this Adama transform of this minus bit, so this is basically already done here, and this is the same as if we basically if we substitute the values here which we would have, this is the same as 1 over square root 2 times the input and f of x, because if we know that this evaluates to 0, then we know that b will be 0 and we don't need to add this here, so no x or b, just nothing, it's 0. Minus, so this is the same, minus the input we get from before, and now we know it's 1, so basically we add x or 1 to this function output here. Okay, so I will not, I'm not going to write this down precisely, but you can write this down if you're interested. And actually what happens is, and this is the interesting thing here, what happens is that the same function here evaluates to this output here if f of x is 0, and it evaluates to this output here if f of x is 1. And where we add this 0 doesn't matter. If we add it to this representation here, to the weight, it basically has the exact effect we need. Okay, because now what happens is that an input of this form gets exactly mapped to this output. Okay, because this here, so this representation is actually the same as this representation, just without doing this exponent. And this is now the thing, that basically we have a function which does this to the right element without knowing the right element. This is the abstract part maybe here. This is implementation of phase inversion, of our first component on a quantum computer. Okay, we are almost finished, but we need one last component. We need this inversion about the mean. But first let me ask if there are any questions to this phase inversion. I hope I didn't make any mistakes when writing this down, because it should be correct, I think. Yeah. Okay, so that's this the first part. And the second part, inversion about mean, we also need this. So remember what we want. We want to have an input like this, equally to the phase inversion, so the input is always denoted this way, and we want that it is mapped to this output here. So basically we want this here, this computation with the amplitude, the probability. And the quantum circuit representation of that is basically this. And now I know that this is confusing and not immediately clear if you see this, what this actually does. So let us think differently about that, and we will then see that this is actually the correct quantum circuit which does exactly this. Okay, so let us think differently about it. Well, first, this u function, this large u function, will return 0 if x is the all 0 vector. So if the input of the function is the all 0 vector, and it will return 1 otherwise. Again, we will see on the next slide, or the next two slides, why this is the case and why it's important and why this is actually correct. Because in this form, this still doesn't explain a lot. So let's approach the problem differently. And it turns out that the inversion we need, this inversion about the mean, is actually the same as the reflection about the uniform vector in this space here, in this space. Okay, and the uniform vector is essentially a vector of all states, but where each state is has the same probability. Okay, this is the uniform vector. And if we denote this uniform vector by some arrow here, okay, so it's just for simplicity that this is 45 degrees and this is exactly vertical, so we can also shift this, it doesn't change the result. But if we now denote this uniform vector by this arrow and this input vector or some vector by this arrow, then basically if we take the orthogonal line here and we flip it here, we reflect it, then this will be, and we will see on the next slide, Sorry, there was a question on the YouTube channel about the runtime. So if the algorithm, if it's true that the algorithm has a 50% chance to give us the correct value in square root n time, since the sum of all other probabilities would be 50% as well. Yes, this is true. And yeah, this is true. Yeah. So this is approximated essentially. Yeah. And actually, I think it's not really the case that if we apply this multiple times, that the amplitude gets larger. Yeah. But this is true. Yeah, it's a good question. So it's not that we get back deterministically the right answer. Okay, so so this reflection, how is it done? Well, first we need to transform this uniform vector to the zero vector, because we use that for our function with the all zero vector. Then we need this reflection, because we will see then that this is actually the same as the inversion about the mean. And then we need to transform back in order to not destroy anything here. And the function which does this is exactly this one, which is Adama at the beginning and the end, and then this matrix in the middle. We'll see why on the next slide. But what this matrix does intuitively, if we have basically a vector which has, if I have a superposition of all states, then the states are ordered, and the first state is 0, basically, okay? Then this matrix will actually return 0, because 1 times the 0 state plus 0 times all other states. But for all other states, okay, except for the first one, this function will actually invert the state. Okay, this is where the inversion comes into play, or the reflection. So this is what this matrix does here. And why does this work? Well, we need some algebra for that here. So this is the function we have. This is exactly the one we have here. Okay, but actually this is the same as, so we can replace that by basically saying that's the same as this matrix here, okay, where we only have basically a 2 here, so plus 1 in the diagonal, minus the identity matrix. Okay, this is the same. And then the next step, what we do now is, well, we can basically move this identity out, and if we do this, we have well, this representation here, minus Adama gate identity Adama gate, and this is again the identity, and this is actually also another property of gates we use in quantum computing, that we can always use this notation here. Okay, and what this is at the end, so we just leave this as the identity, we replace it by I, and we compute that. So this is again an Adama gate. So this is this notation here. Tensor product n means it's basically the tensor product of n of small n Adama gates. So the dimension of this matrix gets exponentially larger. This is all what this means here. We do this n times. It's very similar to this qubit case where we build a tensor product with different qubits. Okay, what this does is, when we have this matrix and we can compute it, we will arrive at the same result. We have this matrix, and this is actually the same if we do the Adama gate again. So if we just matrix multiplication here, this is then this matrix minus 0. Okay, this is just normal matrix multiplication, no quantum stuff here. And where now this minus 0 is the last, the easy step here, we just subtract 1 in the diagonal, so we get this final matrix here. And you may ask yourself, well, why does this do inversion about mean, and how does this even help us? We just get a huge matrix now, and this looks quite random. However, it's not really random, because, well, if we take this matrix, and if we multiply an amplitude vector, a vector of weight with this matrix, well, what happens? We have weights alpha 0 until the last weight, alpha capital N minus 1. Well, we do alpha 0 times 2 over n, plus alpha 1 times 2 over n, plus alpha 2, blah, 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 plus last alpha times 2 over n. So we basically have 2 over n times the sum of all alphas. But for the first alpha here, for the alpha we are actually computing with now, we also do minus 1. So if the sum over all alphas multiplied by 2 over n minus alpha 0. The same minus alpha 1, and so on. And then the same again minus alpha n minus 1. And we note here that 2 over n times the sum of all alphas is actually 2 times the mean. So what this means is that this here, so every entry of that is basically 2 times the mean minus alpha I, and that's exactly what we need. So we need that each alpha I is transformed into this representation. Okay, so if this was a bit too fast, well, the slides on the website, you can just try to compute it with small dimensions, and you will see that this turns actually out to be true. So this is what we need. This quantum. It seems a bit confusing at the beginning, but at the end we now see, well, actually it works. Okay, so that's exactly what we need. We now have a phase inversion, we have inversion about the mean, and we know how it's actually implemented on a quantum circuit. And well, here we have it, and that's the whole quantum circuit for Grover's algorithm. It's essentially only that. So basically, putting together the two components, we have first the initialization step, and with the Hadamard gate. So this is Hadamard gate. So this is often used. The input is basically deterministic qubits, so to say. They get transformed or they get put into a superposition by this initialization quantum gate. Then what we have is this phase inversion from before. So I've ignored the control bits here for simplicity, but we can think about this covering here all 5 lines. It doesn't really change much. So we have this phase inversion, and then we have the inversion about the mean. And this is one iteration of Grover's algorithm, and we need approximately square root capital N such iterations in order to get the correct answer with a high probability. So that's basically it. Okay. So a summary of this algorithm, because, well, yeah, this is very important. So we need around square root N iterations. But what about the cryptanalysis part? We didn't talk about cryptanalysis. This was all about finding an element in a list, which is not necessarily related to what we want to achieve actually. But it turns out that this is actually exactly what we want to achieve. Why? Well, this function f of x, we can also say that it returns 0 if AES with the key x is not a known ciphertext for a known plaintext. But this function returns 1 if AES with some key x is indeed a known ciphertext C for a known plaintext P, so for a known pair, if this actually is true, this relation. So now this is the matter. We need an implementation on the quantum side of this function here, which basically takes a certain amount of input bits and which returns a single output bit. This function, however, is very, very easy to implement in a classical computer. It's just AES. This is not hard. This is not a hard bug. And also in a quantum computer, it turns out to, well, there are various implementations available, but this is actually not what we consider part of this complexity. And what we can also do is we can, for instance, transform this circuit into a hash algorithm. We can say that it returns 0 if the hash of some input x is not the, if the hash of some input, is not the digest we want to have, and that it returns 1 if the hash of some input is indeed the output we want to have. So basically this can also be used for pre-image search to hash functions. And this is all the same. It's all the same to this finding one element in a list. This is all the same in a sense. Okay, so what is the countermeasure? Well, this is not so hard indeed. If we have basically if we have a quadratic speed, so instead of capital N we need square root of n steps. Well, what you do, you just square this capital N. And in bit terms, this means that, for instance, if we want to have a 128-bit security for some cipher, then we would use a 256-bit key. Okay, because basically then the bit size is halved due to this attack, and you arrive at the 128 bits. Of course, ignoring other attacks and other properties, just focusing on this one here. Okay, there are also some combinations available with Grover's algorithm. For instance, there's a combination which works nicely with the Simon algorithm, so not the block cipher Simon, but actually a quantum algorithm against the FX construction here. For instance, this is come in this paper here. Okay, so this was the first main part. Are there any questions to Grover's algorithm, or even to the previous parts also? Okay, then we'll come to the last part, which is quite a bit shorter, because yeah. So this is Shor's algorithm. It's very so the purpose is similar in that we also try to find to attack something, but in that case we try to attack RSA by basically applying this integer factorization. And this is actually a recap. This is a slide which was copied from a lecture of the cryptography course from the previous year. So basically, this is Shor's algorithm. We try to choose a random A, we compute the GCD, and in case this is not fulfilled, we continue. And then we need to find basically this famous R here. And it turned out that basically if A to the power of R half is equivalent to this model, then we cannot use this. But if it is not the case, then basically we can compute GCDs, and hopefully this is then a factor of n. But the thing was, how do we find actually this R? So how do we find this? Because if this would be possible here, then we would already be able to do this on a classical computer. And just trying every exponent here is very, very expensive. And there was this mention of quantum Fourier transform. That's actually how it's done. And I will now shortly explain why this works. I will not go into the detail of the quantum Fourier transform. Okay, why does this work? So first we want to find some R such that this relation is fulfilled. Why do we want to why do we want to find it? Well, we can reorder, and then we have so by just here factoring, we have this one here, and basically if we then compute this or this, it is likely that we have some factors. So there may be some problems. For instance, we could get the wrong factors, or R could be odd. If R is odd, then this is not good for this R over 2 here. But it turns out that for some random guess A, so if we guess this random index here at the beginning, turns out that there's actually a quite good chance that these two problems do not occur. Okay, which means that the biggest problem remains: how can we find R? How can we find this R? And that's where, in this case, quantum computing comes into play. And the general approach is very same as the approach before with the Grover's algorithm. So intuitively, we input all possible solutions, whatever they are, doesn't really matter. We input all possible solutions, and then we try to find a quantum circuit which arranges or rearranges the qubits in a clever way, such that the correct solutions become more likely towards the end of the computation. Okay, so this is the thing we want to achieve. And then at the end, we do this measurement, which is the only non-reversible operation we have here. And hopefully we obtain the correct solution if it had a sufficiently large weight. So this is the intuitive approach. And the high-level approach is, the high-level approach is this one. Let us assume that we have some random exponent, and well, actually we don't need to know R for that to be the case, so you can just ignore this line here. But let us assume that we have some random exponent, then of course it holds that A, so this random guess at the beginning, to the power of this random exponent is some multiple of n, we don't know it, plus C. So we want this C to be 1, right? But okay, we don't know it yet, what it is in order to be 1. But of course it will be some multiple of n plus C. So this will be the case here, of course. If we add now to this exponent the R, which we don't know, but if we would add it, then the result of this computation would be this one, which basically is another factor of n, so some other one, plus C. Why plus C? Well, these factors come from these combinations here from the product, but the C comes from 1 times C. And the same is actually also the case if we add this r again. So if we have a to the power of 2r plus x. Again, we have something here. We have some other factor of some other multiple of n plus the same c again. So in each of the case. And what this means is that the r we are looking for has some kind of repeating property. Okay, because essentially you can think about these states, or these x plus r and so on, being part of the states which are in superposition. Okay, and these states, so r to the x, r to the power of x plus r, r to the power of x plus 2r, and so on, these are all multiples of n plus the same c, the same remainder c. Okay, so this is the important part here. So the thing is, can we somehow end up with a superposition of only the correct powers of these? Okay, because if this is true, then we know that all the powers which we measure, which we get out then, are actually exactly r apart from each other. Okay, we don't necessarily need to know r, we just need to know these powers, because then we know that there are r apart from each other, and r is exactly the number we're looking for. Well, the frequency is then 1 over r. This is the frequency of this wave. And it turns out that, well, we know this, or we know that the Fourier transform is a very good approach to filter out these frequencies. So basically, the input is sum of frequencies, and the output is basically all the different frequencies filtered out. So this is what the Fourier transform does, and the quantum Fourier transform works actually in a similar way, but it's just applied to the qubits in this case. So again, I will not go into the detail why this works. This is a bit more complicated than just this. But essentially, it's similar to the behavior of a normal classical Fourier transform, namely that we try to filter out the frequencies we need. The frequency we need is exactly this frequency here, because if we have it, then we know that all the powers are exactly r apart from each other, and we can basically compute r from that. So this is how, in a bit more detail at least, how Shor's algorithm works, essentially. Okay, so however, this is a big difference to Grover's algorithm. We have an exponential speed up here, which means that many currently used protocols are broken. So it's, if you remember, in Grover's algorithm, we could just double the key size, which is not very expensive, and we would achieve the same security level as before. But here, if we moderately increase the key size of RSA, for instance, of some instance, then this is not sufficient. Okay, so this is a big difference here. So what we like to, so of course, if we increase the key size in a very, very ridiculous amount, then this may work. But just doubling it, for instance, will not work. So the thing we try to do is we try to build new protocols which basically don't allow this method to work. And this is now closely related to this PQC lecture from the cryptography course last term, where I think some schemes were presented which are not vulnerable with respect to this approach. So new signature schemes which are not vulnerable against these quantum approaches. But what is maybe also important to say is that currently we can only factor numbers of around 4 bits. I think, I'm not sure, but I think 21 is still the record. I'm not so sure. But yeah, a couple of bits, we are still far away from the key sizes which are now used for RSA. But still, we don't know. Okay, so a summary of this lecture. So all of that is closely related to quantum physics. So if you want to dig deeper into it, so what is a qubit? Why exactly has each function each function to be reversible? Then I suggest reading up on quantum mechanics and quantum physics, because it's explained in more detail, and there you can also find out, for instance, what a qubit actually is. So it was just a term here, but what actually is a qubit in the real world? And well, yeah, we use these special qubits instead of the bits, and the algorithms are, this is a bit hand wavy here, but they're actually built such they modify the qubits in a clever way. So that's what a quantum circuit does. And the thing is that we want to to rearrange them in such a clever way that at the end the correct solution has a very high probability attached to it, or at least much larger than the wrong answers. So we measure the end and we hope that we get the right probability. However, currently it's not a threat, not a big threat, these quantum computers, but who knows about the future, so it's better to adapt and to try to build schemes which are not vulnerable, or at least which we believe not to be vulnerable. Okay, so this was it, essentially. Um, Thanks. Do you have any questions left? Okay, just to say, don't just go away because there is also the presentation of the first assignment, which will follow in, I don't know, maybe 2 or 3 minutes. So even if you don't have any questions anymore, you may still be interested in the presentation. Okay, so if there are not any questions from your side, I'll just minimize this and open the presentation slides. Okay, it should work, I think. Okay, well, so this is now a different topic. So this is basically a presentation of the first assignment you have to do for the practicals in this course. And the first assignments will be about asymmetric analysis. And many of the topics you already have heard about in previous lectures, so I will skip the detailed explanations. But there's also a new topic, which I'll maybe explain in a bit more detail, which will also be explained in the next lecture. So there will be something here which you don't have heard about yet in this course, but don't be afraid. You will hear about next week. So, okay, but since this is the first assignment, first some overview. So the goal is essentially to implement the text from the lecture in teams of 2. And in total, there are 2 assignments, and each of the assignments has 3 tasks. But the first task is an easy one, the second one is a bit harder, and the third one is normally the hardest one, so to say. Okay, you can get 48 points, in total, so which is actually, so this is 24 times 2, but 100% is actually 32 points, which makes it a bit easier to get a good mark. Okay, so this is about the grading scheme or the assignments. So the first one will be about asymmetric cryptanalysis. The release is today, and today is actually also the deadline for the team registration. And so yeah, please make sure you've registered. And the question hour is on the 22nd of April, and finally submission will be on the 29th of April. And I hope these dates are correct. Well, they should be because there's 21 here. But, so the first date is I'm pretty sure this is correct. Okay, so what about the tasks? The first one is the winner stack on RSA. You have already heard about that in a previous lecture. And the goal is basically to implement this attack to recover the exponent of some instantiation of RSA, which has a low priority exponent, or a small one. Yeah, there are basically 2 subtasks, which are given here. And yeah, that's basically the idea. I think this very example is included already in the lecture, if I'm not mistaken. So I will skip it here. You should already have heard about that. So that's basically the first task. It's this attack on the RSA. The second task is something you haven't heard about yet in this course at least, and it's an attack on a padding oracle, which is called the Bleichenbach's attack, or one variant of it. And this is also split into different subtasks. So the first task will be to implement RSA with this padding scheme. And now this basically sounds worse than it is. This is actually not so. This is only a plain implementation of RSA with this padding scheme and with this 0002 oracle. And we'll see in a minute what this actually means. This is actually not so hard. But the main part will be this one probably. So the second subtask to essentially implement the CVP solver using this special rounding technique here. And I will also come to it later in the hints, but essentially this algorithm here uses, internally uses an LLL algorithm or works on some basis which is supplied after the LLL algorithm, but you may use an existing LLL implementation. So of course, if you want to implement your own, we don't want to stop you from that, but you may use an already existing one. And yeah, CVP stands for closest vector problem. We'll see about that also. And the third subtask is finally to basically build the attack. So to use these two components and to basically mount the attack. And yeah, so as I've said, this is new. This will be covered in next week's lecture. So I will not explain the whole terminology in detail now, but just give an overview of the attack. Okay, so how does this work? First, we have this PKCS padding scheme. And this works such that basically we generate, we input a message M in the RSA, and we then append or prepend these bytes here. Okay, and basically for some bit size of RSA, we subtract the message size in bits. So then we have basically the number of random bytes we need to add, -3 because of these 3 bytes here. And this is then the padding scheme. And this thing here, the whole thing, is then put into the RSA algorithm and is encrypted with RSA. So this is padding and then encryption. And the thing is here that if we send some ciphertext, some encrypted, some ciphertext to an oracle, we basically let the oracle decrypt it. Then if this is not if the result of the decryption does not look like this, then the oracle will report some error. And this is this 0002 oracle I was talking about before. Okay, so how does the attack then work? Well, we recover, the goal is to recover some message M from the ciphertext of this message. Okay, so this is padded here already. And basically, yeah, let us just go to the attack itself. So basically it has a loop, and the goal is to recover this ciphertext, this message, sorry, by constructing these ciphertext here, this edited ciphertext, so to say, for some random values s. And this oracle, this PKCS oracle, returns basically true or false, whatever you decided to return. This is up to you. But basically the answer is based on these first 2 bytes, so whether they are 0002. And essentially the thing is that you will be successful in this step for particularly chosen S with a probability of approximately 1/2 to the power of 16. Okay? And the thing is that you repeat this step until you have sufficiently many values of S such that for all of these values of S, this oracle answer was basically true or successful. So this is this step here. And it turns out that this is very similar now, if we collect these values, to the so-called hidden number problem, where we basically know some bits of a number, so some initial bits, for instance, but we don't know that part, and the hidden number will then be basically our our m didn't. So this is very similar to that. And the next step in this attack is then to set up this lattice. And again, the lattice will be part of the next lecture, so it's not yet covered here. And if we have this lattice, we can clearly see that this unknown vector, so this m times 2 to the 16 and these things here, that this is actually part of the lattice. Okay, we can see that this is an element of the lattice. What we also know, so we don't know the vector, this vector we don't know it, but we know that it's an element in this lattice. It can be constructed from this lattice here. But what we do know is this target vector t, which is constructed so using these relations here, which is constructed such that this is very close to this m. And now we hope that if we input this lattice, which we can do because we know all these values, and this known target vector, we hope that if we input this into a closest vector problem solver, that the answer we get, so the closest vector actually is m, the thing we're looking for. So this vector here. So this is the idea behind this approach. And it turns out that this is very realistic because the difference between m and, so the distance, sorry, between m and t is smaller than, is quite smaller than the average distance in this lattice. And you will also hear about that in more detail in the next lecture. But the thing is that we actually expect that m is the closest vector to t. And this closest vector problem can be solved, for instance, with this Bayes rounding technique. Okay, in practice, for a 1000-bit RSA, we need we need a couple of million queries in practice. And well, this you can also do it for lower bit size, so we'll come to it later. And this is actually also applicable in other scenarios, for instance, in side channel scenarios. So it is not the only application here. Okay, so some hints at the end. As already said, you can use an existing implementation of the LLL algorithm. So for example, Sage has one. I think, so I'm not so sure because at least I didn't find it. But I think this works only over integers or over Q. But that's fine, so it should still work. A hint is also to test your implementation of this CVP solver using small lattices. So what you can do, for instance, you can create an integer lattice in Sage, then choose some element in the lattice, so some real element in the lattice. You can add a small offset, and then you can start the CVP and hope that you get back this element. So that's what you can do, for instance, to test it. And yeah, another thing which is maybe good is to start with small RSA moduli, for example, around 100 bits only. You can then increase it. So this should be finished very, very fast. So at most a couple of seconds. Okay, but again, all of this will be explained in more detail, especially the notations here in the next lecture. Okay, and finally we have the last problem, and the last problem is about factoring, and this was also part of I think the first lecture. And basically it's also split in 4 subtasks, which on the final goal is basically to factor also some number n here with this technique. And again, if I'm not mistaken, I had a very quick look to it. I think that this approach is more or less in the same way explained already in the lecture, so we'll not go into too much detail. I will just skip the detailed approach here. But essentially just refer to lecture 1, which explains these steps. And yeah, so this is the last subtask of the first assignment. Okay, yeah. So so this is important. So for the rules, you can pick your favorite programming language. Doesn't really matter. Don't let it be some very strange one. But other than that, it's always fine, I'd say. But you will need some support for big integer and modular arithmetic, so it's maybe good to use some language which has built-in support for that. And yeah, so some number theory functions, etc., linear algebra are recommended. You can write it all yourself if you want to, but yeah, it's maybe easier if you pick a language which already includes it. So suggestions are, for instance, Sage, which is essentially Python for the math parts, but also C or C++ have many math libraries, so NTL, GMP, and so on. And for the submission, please please submit 3 zip files, and each of the zip file or zip archive should contain the code of one of the 3 tasks in this assignment, 3 files in total. And please also add a README file. You can decide whether it's a Markdown file or a PDF file on the top level to just explain, for instance, the difficulties you had, the limitations of your implementation, and also maybe if you made some choices. So, for instance, regarding the size of some numbers. And especially if you do it with C or C++, please also include a makefile or very clear instructions. So makefile is not really required, but then at least some very clear instructions how to compile the program and how to run it. And this helps us a lot. Okay. Yeah, so the deadline is the 29th of April, 2021 of this first task, so it's in a bit more than a month. And please upload your submissions to the STIX system. And yeah, this is essentially 1 zip file per task. And please also tick the task and the tasks which you solved at the end, or partially. Are there any questions to that? Also organizational questions. So if not now, of course, you're allowed to ask anytime you want, either in the lecture, but also I think this is from the previous year, so maybe it's better to ask for the Discord channel. We will upload these slides here also and replace this so you can see it. But yeah, exactly. Yeah. So this will all be uploaded on the website very soon. And of course, you can also ask your colleagues if you have trouble with some of the tasks. Okay. So if there are not any questions anymore, I will still stay here for like 5 minutes maybe. So if you have some question, you can ask it. Also, of course, to the lecture about quantum cryptanalysis, if you have any questions. I'm still here for a couple of minutes, and yeah, if you don't have any questions, then thanks for your attendance and good luck for the assignment. Thanks.